This video is one of two videos that I have made on the subject of this simple resistor-capacitor circuit powered by a constant electromotive force, also known as an EMF. The two videos are meant to complement one another. This video focuses on the math. The other video focuses on the physics. For this video, you'll need a solid background in basic calculus, and that means derivatives and integrals. It couldn't hurt to know about basic electric circuits as well. All of this stuff should look familiar: charge, current, potential, resistors, and capacitors. If you don't have this physics background, I can only assume you're here because you're in a differential equations class and some problem showed up in the curriculum that resembles this. And if that's the case, you should know that it takes the physics students weeks to get up to speed on this stuff, so you're not really going to understand it. But if you can follow the math, maybe that's good enough. Now we're going to have our hands full doing this math, so I'm going to gloss over a lot of physics details. In my other video, I don't do any calculus or even really any algebra at all, so I'm going to have time to talk a lot more about the physics. So if you have unanswered questions from this, you might find answers in that other video. You can find a link to that video, should be up there or in the description down below. And also this list is in the description down below with timestamps, so you can skip ahead if you like. So we will start from this and use it to set up the differential equation. Then we'll solve the differential equation, and we'll look at different versions of the solutions. These two I cover in that other video as well from a different perspective. This, on the other hand, I only do in this video. So we start by considering what's going to happen when we close this switch to complete the circuit and allow current to flow. Well, the formula for the voltage on the resistor can be rewritten thusly. Since the current is just the flow rate of the electric charge, and we can rewrite the capacitor voltage this way. And if we substitute these into here, we get that. That is the differential equation that we want to solve. We're looking for some kind of formula for Q. Q presumably is some kind of function of time. One more thing to mention, I'm going to include an initial condition. The charge when t equals 0 will be equal to Q0, which will be some number, whatever you want it to be. So there's the problem we are trying to solve. Let's rewrite the differential equation in the following way. All I did there was divide everything by r. And that got me a differential equation in a standard format that looks like this. So all this means is that's all that's going on there. It's a good idea to streamline equations in this way when you can, because it makes the algebra easier. So what do we do with this? Now most people like to solve this equation using the method of separation of variables. But I'm going to do something different. I'm going to use a trick called an integrating factor. E to the integral of a dt. Whenever you have a differential equation in this form, first order linear equation, the integrating factor will always work. And this coefficient right here is what goes right up into there. So the integral will just give you at. So there's the integrating factor, e to the power of a times t. You don't want to add an integration constant there. It doesn't help. What do we do with this integrating factor? Let's multiply all of the terms by the integrating factor. What good does that do you? There's a pattern here. Do you see it? There's an x prime, and there's an x. And then we have these two functions. Do you see a pattern with them? Well, this is the derivative of that. Does that look familiar? That should look familiar. That's the product rule for derivatives. Do you see the connection between this and this? Well, if this is the derivative of that, we could call this g prime, call that g. Now, x prime is the derivative of x, so we could call that f prime and f. And as you can see, the left-hand side of the equation is a perfect match for this product rule. And that's the whole point of the integrating factor. When you do this, you automatically end up with this expression that perfectly matches the product rule format. And of course, the antiderivative of f prime g plus f g prime is simply f times g, so it's easy to integrate this left side straight away. It's simply going to be f, which is x, times g, which is e to the at. Now the right side will take a little more work. Whatever it is, it's going to be that. So let's integrate this right side. Don't forget your integration constant, and I'm going to call it k since c is already in use. So we're getting close to a solution. All you have to do now is divide by the integrating factor. And then we can substitute back to our original quantities. I skipped a little step, but you should be able to verify that b divided by a is in fact equal to c times e. So we're almost there, but we need to nail down what this constant is. And that's where our initial condition comes in. So if we substitute q equals q0 and t equals 0, we get e to the power of 0 is 1. 1 times k is k. So there you have it. There's the value for k, and then the solution finally becomes, there is our solution. There's the differential equation. There's the solution. Now let's look at some specific cases. So the first case is when you're charging the capacitor. In this example, we assume that the initial charge on the capacitor is 0. There it is. And then the electromotive force E is whatever it is. What is this formula telling us? Well, when we let Q0 equal 0, this simplifies. So I let Q equal 0, and then I factored out a CE. What would a graph of this look like? Well, we already know the initial value for Q is 0. So that starts right there. This exponential function is going to approach 0 as t becomes large. 1 minus 0 is 1, so we get 1 times CE, which is CE. CE is the maximum value that this capacitor charge is going to attain, and we're going to approach it asymptotically like that. When Q equals CE, the potential on the capacitor is equal to E, and when this potential drop and that potential drop are the same, the potential drop across the resistor becomes 0, and there's no more current. When there's no more current, the charge remains steady. Now what about that current? Well, the current is the derivative of the charge. If you take the derivative of this expression, you will get. Once again, I skipped a little step there, but you should be able to figure out where this coefficient comes from. What does that graph look like? The initial value of the current occurs when t equals 0. E to the 0 is 1. 1 times E over R means we're going to start right here at E over R. And this is a decaying exponential that approaches 0. So there we have our decaying exponential. So far I've shown you 2 formulas and 2 graphs, but there's more to the story. You could write a formula for VC, and it's easy to get. Just take this formula for Q and divide by C. So for VC, you will get a very similar formula and a very similar graph. Over here, VR is equal to the current times R. So take this formula and multiply by R. And again, you'll get a similar formula and a similar graph. So you should be able to find those yourself. And once you've got all 4 formulas and all 4 graphs, you've got a complete description of just about anything you could possibly want to know about what's going on in this circuit. Let's look at the next case, discharging the capacitor. So in this case, we assume that we start out with some potential on the capacitor already. So there will be some charge there, and we'll have a non-zero initial charge on the capacitor. And then we're going to drain or discharge the capacitor. If the EMF is equal to 0, then the circuit that we're really looking at is that. Again, we'll start out with plus Q0 on the top and minus Q0 on the bottom. So letting E equal 0, we get to there easily enough. We have a very simple graph that looks like that. That seems simple enough. What about the current? When you take the derivative, you get that. This looks a little odd. We have a negative coefficient, which means our graph is going to look like this. It starts out at a negative value and then approaches 0. What's that all about? Why is it negative? Well, consider this up here. In the first example that we did, we started out with an uncharged capacitor, and then we let the current flow, and presumably it would have flowed in this direction so as to accumulate positives on the top and negatives on the bottom. But in this circuit, the capacitor is the voltage source. With positive on the top and negative on the bottom, you're going to get current, when you close the switch, current going the other way. Well, if a clockwise current is positive, it makes sense that a counterclockwise current would be negative. So what about VC and VR? So it's easy enough to get a formula for VC. You get a similar formula and a similar graph. And over here, you'll get a similar formula and a similar graph, which means that VR is also going to be negative, just like the current. What does that mean? Well, in our first example, as the current flowed clockwise, that meant that the current through the resistor would be from right to left, and you always get a potential drop as current flows through the resistor. If you reverse the current, you're going to reverse the potential drop. In my other video, I wrote out all 4 formulas, and I drew all 4 graphs, but I made these positive just to keep things simple. So let's look at this general case now, where neither quantity is equal to 0. What does the graph of this look like? Well, we can see this decaying exponential is going to approach 0. So this whole term will approach 0, and Q will approach CE asymptotically, like we've seen before. So everything is going to approach CE. Let's look at a few special cases. Suppose Q0 is less than CE. That would put it right about there. What's it going to do? Well, it's going to climb and approach the asymptote like it always does. But what if Q0 is a lot bigger? What if Q0 is actually greater than CE? Well, in that case, it's going to start out here somewhere and then go down. That's what would happen if the initial charge on the capacitor was so great that this potential here was actually greater than the electromotive force. And if that were to happen, then the current would actually flow counterclockwise to partly drain the capacitor until eventually it approaches Q equals CE. Now there's one other case actually to look at. I assumed without saying so that Q0 was positive. But what if Q0 was negative? Well, then it would be down here somewhere. And the formula says, once again, it would approach the asymptote. Now what would that even mean, a negative Q0? Well, up until now, we've always had a positive Q0, and we've always had positive charges on the top and negative charges on the bottom. But the charge in the capacitor could be whatever you want it to be, and there's nothing to stop you from putting a negative charge on the top and a positive on the bottom. And if we reverse it like this, that will make this a negative Q0. So what will happen is we'll have a fairly large negative charge on the top and positive on the bottom, but both of those will approach zero, and then as it passes through zero, the charges will flip and you'll get positive on the top and negative on the bottom, and then we'll continue like we did before. So you can see case A has us charging the capacitor. Case B has us discharging, although we're not discharging down to zero this time. And then case C has us actually discharging and then charging. So what about the current? When you take the derivative of Q and tidy things up a little bit, you get this. Again, I skipped a step. What does this graph look like? Now this whole coefficient in front here is going to be the initial current, whatever that happens to be. Let's look at these three cases. If Q0 is less than CE, then CE minus Q0 is positive, and this whole coefficient is positive. So the current starts out somewhere around here, and then we're going to approach zero. What about case B? If Q0 is greater than CE, then this becomes negative. So then the initial current is negative, and we're down here. And again, we approach zero. Case C is similar to A in that Q0 is definitely less than CE, but we're going to be up here somewhere and then go down like this. And I know that C will be higher than A because for case A, CE minus Q0 is the distance from there to there, whereas for case C, CE minus Q0 is the distance all the way from there down to there, which is clearly bigger. So the initial coefficient will be bigger for C than it was for A. And of course, since the current is equal to the derivative of the charge, A and C will both have positive derivatives because they have positive slopes, and there they are. B will have a negative derivative because it has a negative slope, and there's B down there in the negatives. And so it all makes sense. Now, if you're really a glutton for punishment, you could do this all over again for VC and for VR. So if you made it this far, please like and subscribe. Also, if you are interested in being tutored online by me personally, I'm available. This is my website, alternaprof.com. There's a link in the description down below. And here's a couple more videos for you.